Our recording, this is the 19th of May, and this is the 13.3 practice sheet. We're going to go over some of the concepts here. All right, so on the first one, you're told that you're given a saturated solution of iron 2 bromide at 20. What's its molarity? And actually, you know what? You don't even have to. I added that it was 500 milliliters of that solution. You don't even have to know that, actually. You don't have to know that. So let's do it with the 500, but I realize, yeah, you don't have to know that. So if we assume that we have 500 milliliters of this solution, and we're going to assume for right now, and I'm going to say this is slightly sloppy bookkeeping. It gives you rough answers. The precision is not high here. If you're going to miss 500 milliliters of this solution, so we have 500 milliliters of solution. We know that, and if we're assuming that most of that volume is just water, so we're going to pretend that the solute isn't adding any volume to it, then we can say, okay, well, 1 milliliter of water weighs 1 gram, and we know that in 100 grams of water at 20 degrees, we go up to our chart, we can dissolve 124 grams of the iron 2 bromide, FeBr2. So far, so good? So now we can find out how many grams of iron 2 bromide we actually have in there. And that would be 620 grams of iron 2 bromide. Because obviously, if we're going to talk about molarity, we need to know how much solute is in there. So one of the first steps is to figure that out. Okay, well now we know how many grams of iron 2 bromide are in. Well, in order to figure out the molarity of the solution, if you remember, molarity is equal to the number of moles divided by the number of liters of solution. So this is what we want. We have the volume of solution, and we need moles to figure that out. You guys are pros at this point at going from mass to moles. That's just a simple stoichiometric conversion. So, start off with our 620 grams iron 2 bromide. Molar mass of iron 2 bromide, and I'm not going to figure it on here because you guys know how to do that part. 215.65 grams. Whoops. Of iron 2 bromide comprise 1 mole of the same. Gets us is 2.87502, etc., etc. I apologize, my writing is terrible with this particular stylus. 2.87, good lord, that is bad. Let's see if I can do any better. 2.87502, etc. moles of the iron 2 bromide. Well, now we have all the pieces we need. We have the volume of solution, and we have the number of moles. So the molarity is going to be equal to 2.8752, etc. moles. How many liters of solution do we have? 0.5. 0.5, right. So we get a molarity of, our raw answer is 5.750057964 molar. And with sig figs, we would be able to say, and this one's, if you have the printed copy that has 500.0 milliliters, that means you have how many sig figs? 4. You know, and whether we should use the value in the chart is sort of an open question. Typically, we don't use lookup values. We kind of assume, well, no, we should. Okay, so based on that, I would change the number of sig figs that I had on the key, and I would say that the final molarity is 5.75 molar, which is pretty concentrated solution. So when we did the production of hydrogen gas in the BRETs and we did the concentrated hydrochloric acid, you remember that? We layered acid over water. That was 6 molar hydrochloric. Do you remember how nervous I was about all of you handling 6 molar hydrochloric? Yeah. 5.75 molar is pretty concentrated for any solution. Like 6 molar hydrochloric acid, we are super crazy careful with. I don't know what the molarity of stomach acid is. That's an interesting question. Somebody should find that out. I'm sure somebody knows. Okay, if you were not given a volume, could you still solve this problem? Especially considering I said earlier, hey, you know what, we don't actually need the volume. You might guess yes. Okay, how would that look? So this is number one done an alternative way. If we were not given a volume and we were just told, okay, you've got a saturated solution of iron bromide at 20 degrees Celsius, what's the molarity? This is kind of like when we were doing empirical formulas and you made up some amount of mass. You know, there you had like an imaginary 100 gram sample. Well, here you can have an imaginary 100 milliliter sample. You know, you just automatically pop into, oh, okay, let's say I have 100 milliliters of this stuff. Well, 1 milliliter, 1 gram, and we know that for every 100 grams of water, and we're cheating and assuming that most of the, I'm not sure where it cut off, but we know that for every 100 milliliters of water, that's 100 grams of water, and for every 100 grams of water, we can dissolve 124 grams of iron 2 bromide, which really is just a long way of saying in this amount of solution we have hi Jason, hiding really effectively behind James' head. Hiding really, okay, well, being blocked really effectively by James' head. Okay, where am I going to sit you, Robbie? Where am I going to sit you? Don't know. So we know that in 100 milliliters of solution we've got the 124 grams of iron 2 bromide. Well, now we can look at how many moles is that. So 124 grams iron 2 bromide. We already found the molar mass, 215.65 grams of the same in 1 mole. And so that would give us moles of iron 2 bromide. Now that's not the same number of moles, but we don't have the same volume either. So we're going to get the same molarity because we have less of the solution. This shrunk. Okay, so now if we go into our molarity problem, we had 100 milliliters, not 500 milliliters. So we have 0.57500, etc. moles in 0.1 liters now. So guess what? We get the exact same molarity, 5.75 molar. Okay? So you don't actually have to have the volume of a solution like that because you can make up that sort of imaginary 100 milliliter sample, and that's an easy way to do those. Number 2 was the crazy one, 8.6 molar iron 2 chloride solution. Is it saturated, unsaturated? I should have added supersaturated to that list of options because that's always an option. There are 2 ways to do this, and I actually like the way that a student came up with better than I like my way. So what one student decided to do was say, well, if I had a saturated solution of this, what would its molarity be? So basically attack it like you did the last problem, and looking at iron 2 chloride at 10 degrees, for every 100 grams of water, we can dissolve 59 grams of iron 2 chloride. So let's figure out how many moles of iron 2 chloride that is. Let's figure out the molarity of just, 100 milliliters of that solution. And then we can compare that to the 8.6. Okay, so 59 grams iron 2 chloride, and the molar mass of iron 2 chloride is 126.75 grams per mole. So we get of iron 2 chloride. Okay, so then if we've got 100 milliliters of solution, what's the molarity of that going to be? And most of you can probably do this in your heads, though I wouldn't recommend doing that on the test. Well, molarity would be equal to moles over liters. Since we were dealing with a little fake 100 milliliter sample here, that would be 0.46548, etc. moles over 0.1 liters. So what we get is if we have 2 sig figs, 4.7 molar solution would be a saturated solution. So is that 8.6 molar saturated? Oh, it's either saturated with chunks in the bottom because things have fallen out of solution. If everything in there is actually dissolved, that's crazy supersaturated. That's, ridiculously, probably physically impossibly supersaturated. Who writes these questions? Anyway, that's I think a much more elegant way to do it. I can show you the other. Did anybody do it a different way, sort of off the top of their head? Yeah, no? Did anybody do it this way off the top of their head? Did anybody do it? Okay, I see one nod. The other way to do it, and the way that I sort of intuitively did it, was, if I had 1 liter of solution, so this is number 2, alternate method. If I had 1 liter of this solution, and it is, hold on. If I have an 8.6 molar solution, I have 8.6 moles in 1 liter. That's by definition. So then I went back and looked at, how many grams is 8.6 moles of the stuff? And then compared that to the number of grams I would have in 1 liter of solution of saturated. You can do it either way. I think this method is more elegant. Does anybody want to see the other way?
I do.
You do? Okay. So, if we have an 8.6 molar solution, we know that molarity equals moles over liters. That means if we have 1 liter, 8.6 molar times 1 liter equals moles, we have 8.6 moles of solute. Okay. Well, that's 1 liter of solution. So now I can go back and imagine that I have 1,000 milliliter or 1 liter sample of this solution. Well, if I know that 1 milliliter is 1 gram, again, I'm doing that cheat, and I'm assuming that most of the volume of this solution is the water. It's a little bit sloppy. It's not perfect, but we're not doing pharmaceutical grade chemistry here. In every 100 grams of water, I can dissolve 59 grams of the iron 2 chloride. Okay, so that gives me 590 grams of iron 2 chloride in a liter of this saturated solution. How many grams is 8.6 moles? Well, 8.6 moles of iron 2 chloride, and the mass of iron 2 chloride is 126.75 grams. That's over 1,000 grams of iron 2 chloride. So clearly, either this is a saturated solution that's got chunks in the bottom because precipitate stuff has fallen out, or it's, against all odds, against all laws of the physical universe, it's holding it and it's supersaturated. Questions on either of those methods?
So what would be the final answer?
Final answer here would just be, either it's supersaturated if everything's still dissolved out, or it's saturated with chunks. And you just have to be able to show me a comparison. So like on that, the way that question is worded, I couldn't even, there's not a sig fig point because there's no numeric final answer. I mean, you have to show me numbers. Like if you just wrote, I have a 50-50 shot, saturated on a test, I'd mark it wrong. You have to show me how you arrived at the answer. You would be amazed. People have tried. You have to show me the numeric way you got to that answer. But yeah, the final answer is just saturated, unsaturated, supersaturated. So if it is something like this again, and I think I've fixed all the crazy problems, maybe one at a time, year by year. If this came up with this kind of number, and you wrote supersaturated, you would be smart to qualify that by saying if it's all still dissolved, you know, because you understand that difference between saturated and supersaturated. Other questions? 9? Okay, let's go to the third one. Okay, what's the molarity of 4 liters of a saturated solution of iron 3 perchlorate at 30? And here we're told that 3.95 liters of that total volume is water. So the first thing we want to do is figure out in 3.95 liters of water, how much iron 3 perchlorate can we dissolve? So knowing that our volume of water is 3.95, we can start with 3.95 liters of water. This is the step that we've been cheating in all the other ones, where we've been saying, oh, the whole volume of the solution is water. We know it's not, but it's a little bit of a fudge factor. Okay, we want to make sure that we're in the correct units to use a solubility table. So 1,000 milliliters is 1 liter. 1 milliliter of water is 1 gram of water. And in every 100 grams of water, we can dissolve at this temperature, and this is at 30, we can dissolve 478 gesundheit grams of ClO4. Okay, what that gets us is a raw answer of 18,881 grams of iron 3 perchlorate. Okay, so that's how much iron 3 perchlorate would be in there. Well, now we need to know how many moles of iron 3 perchlorate that is. Okay, so if we start off with our 18,881 grams, 18.8 kilograms would be a better way to express that. But okay, and we know that the molar mass, I mean, an iron 3 perchlorate is kind of heavy stuff. It's 354.2 grams per mole. So we have 53.306, etc. moles of iron 3 perchlorate. Well, now we're ready to find the molarity. Can you see that? Is it down too low? Okay. So, whoops, at this point, we know how many moles of iron 3 perchlorate we have. So I'll box that off. And molarity is just equal, whoops, be careful. Molarity is just equal to moles over liters. So we have 53.306, etc. moles, and we have 4 liters of solution. Okay, so you get 13.32651,045, etc. molar. With 2 sig figs based on our 4.0 liters, we would just call it 13 molar. 13 molar solution. That's really concentrated. I think glacial acetic acid is like 16 molar. Glacial acetic acid is as concentrated as you can get acetic acid because it starts to draw water from the environment. So there are solutions that cannot go above a certain molarity because they'll suck water out of the environment, basically diluting themselves if you get them up there. So, okay, questions, comments, cookies, quizzical looks? No? Okay. All right. The back, anything on the back? The back, I think most people had a pretty easy time with. On the back, these are all problems. Were you stretching or do you have a question? Yeah, I can do 7, absolutely. Okay, we'll do 7. On these, for all of them, this is kind of like the gas law problems where you're using both the ideal gas law and a factor label. For all of these, you're using both a factor label and the molarity equation. So I always, to start these kind of problems, write this down. If I have everything I need for that, I start there. If I don't have one of the things I need for that, I do a factor label until I get it. And the most common one is you're given grams and you want a volume or molarity, so then you have to get into moles. So that means doing a factor label first. If you're given a molarity or a volume and you want to get to grams, you have to use this first and then do a factor label. So it's just one of those decisions. Do I start with this or do I end with it? But I always write that down first because that tells me whether it's my first step or whether I have to get something before I can use it. Okay, any of the ones before number 7? Anybody want to see any of those? 9? Okay, yes?
Number 6.
Sure. All right. And if, let's do number 6. So in number 6, you are tasked with mixing 375 milliliters of a 0.1 molar sodium chloride solution. How many grams of sodium chloride do you need? If we start with this equation, do we have everything we need here? No. So, well, no. But we want grams. So can we start, so a factor label, typically we're going from moles to grams. Do we have everything we need to start a factor label here to get to our answer in grams? Ja oder nicht? Ja? Nicht? Yes? We have everything that we need to start a factor label? No. What do we need? We need the moles. So here we're going to have to start with this. We have 2 of the 3 things we need, so we can solve for moles and then take that moles, the answer in moles, and put it down into our factor label. Okay, so doing our algebra, molarity times the number of liters will give us an answer in moles. And the one thing I will caution you about again and again and again and again, don't screw up and put in milliliters. It will give you a gigantic decimal error. So we have 0.1 molar solution. How many liters of solution do we have?
0.375.
Yep. 0.375 liters. So we get 0.0375 moles of sodium chloride. Okay, so now we can put that in here, 0.0375 moles. We know that 1 mole of sodium chloride has a mass of 58.44 grams. So we end up with 2.1915 grams. We have 2 sig figs because of our molarity. I didn't put the 0 in there, but in the problem there was a 0. So we would be massing out 2.2 grams of sodium chloride. That's not a lot of sodium chloride. Okay, so it's a tiny, tiny, tiny amount of sodium chloride, but you're dealing with less than a half a liter, and you're dealing with a pretty dilute solution, so you shouldn't, that answer is not surprising. Honestly, from your experience massing things in the lab, massing an amount that small, I think, is tougher than massing a larger amount. I don't know if you'd agree, but those tiny, tiny, tiny little amounts, I mean, that's about the same mass as your massing tray. The little blue massing trays we use are typically about 2.2 grams. So, okay. This is about the most common type of problem because it's the most practical. This is the one that you would actually do in a lab. And if you're going on in chemistry, these are the kind of problems in a quant lab. You're going to do boatloads of these because a lot of time, well, I should say this and number 7. If you're working on the prep end, this is the most common kind of problem you're going to do. If you're working on the actually doing reactions lab end of it, number 7 is the kind you're going to do because number 7 is the stoichiometry of solutions. And most of the reactions that you do, you're working with solutions. You're not working with dry reagents. So you have to think about how much of a solution you need to get the number of grams of solute that you want to react. Okay, let's do number 7. Okay, so we're told that 75 grams of calcium chloride in solution are needed to react with lead 2 carbonate. We've got the reaction. Does having the reaction there matter? Do you have to do anything with it? No. It's a red herring. I could give you one. I once had a question written up that was like my super nightmare evil extra bonus question. And I just gave you the reaction and told you you needed to produce this many grams of a product, how many grams, and you have this much, you have a whatever molar solution, you can proceed from there. I'm not going to do that to you, so we're keeping it light here. Okay, 75 grams of calcium chloride are needed. All that you have in the lab is a bottle of 0.1 molar calcium chloride. What volume of that solution are you going to need? Note that 75 grams is a lot of calcium chloride, and note that 0.1 molar is a really dilute solution. This is probably going to be a pretty big volume number. So the first thing we have to, let's start off as I've suggested. Do we have everything that we need to solve this? So we have the molarity. We want to solve for liters. I'll circle that in some other color. This is what we want to get, is the volume of solution. Do we have everything we need to plug in and get volume yet? What do we need?
Moles.
We need the moles. So we can start off with the number of grams that we were given, 75 grams calcium chloride. How many moles is that? Well, 110.9, whoa, it got worse. 110.98 grams of calcium chloride in 1 mole. So we need 0.67579, etc. moles of calcium chloride. Okay. With that, we have a number that we can put back in here. We need to solve for the volume, which is in the denominator. I mentioned this to a few of you yesterday. So 6 years of teaching chemistry, 5 of teaching physics, and I get the best kids. I mean, I get kids whose math skills are pretty solid. Algebra 1 was a long time ago. You've been using algebra for a long time. Solving for something in the denominator in a 3-part piece of algebra is the single most, I would say that 50% of my kids will screw that up at least half the time. And these are people who are great at math. Like my physics kids screw this up. It's easy to do. If you find yourself making mistakes there, because what people do is they solve for the inverse, and that's a mistake, do it the long way. So multiply both sides by that volume. Then everybody can solve that. I never see a student screw up solving there. And I do it myself. It's easy to do. Screw up solving there. I have to do every step. So then we can divide both sides by molarity, and we've got our solution for volume. Okay, so with the algebra out of the way, moles divided by molarity. So volume is equal to 0.67579 moles calcium chloride divided by a 0.1 molar solution of calcium chloride. We need a whopping 6.75797, etc. liters of this solution. So with sig figs, we would say we need 6.8 liters of calcium chloride solution. That's a lot of calcium chloride solution. That's 3.5 pop bottles. So talking about a lot of calcium chloride solution to get that much calcium chloride. Okay, questions, comments, anything else on these kind?